For today's video notes, you will need IC38 in class 38. This is day 3 of our standard 9 special parallelogram topic. Today's focus is on a new shape, rectangles. The previous 2 lessons have been focused on the special parallelogram called a rhombus. So today we're going to talk about similar things but with a new focus on rectangles. So first we'll start off with the definition. A rectangle is still a parallelogram, but instead of being a parallelogram with consecutive sides congruent, like a rhombus, this is a parallelogram that has a right angle. And so what happens, because a rectangle is a parallelogram, is just like with the rhombus, all of our properties of parallelograms are still valid. So when we look at a rectangle, just like when we look at a rhombus, just like when we look at a parallelogram, we can remember that opposite sides are parallel, which means alternate interior angles are congruent, opposite sides are congruent, opposite angles are congruent. We also have consecutive angles that add to be 180 degrees and diagonals that bisect each other. So all of those properties are still true and can still help us to solve problems. But in addition to those parallelogram properties, a rectangle is special, which means we're going to have 3 additional pieces of information about a rectangle that will also help us to solve problems. So the first of these is related to what we wrote in the definition. If a rectangle is a parallelogram, but it has a right angle, that actually ends up meaning that all of the angles are right angles. They're all congruent to each other if they're all right angles, and that means that they're all 90-degree angles. So those are kind of 3 different ways of mentioning the same type of fact. And the reason for that is that if we're in parallelogram mode, if we just investigate a little rectangle picture real quick, as soon as this angle is a right angle, according to the definition, we know the opposite angle is also going to be congruent, so it's forced to be a right angle. And then we know the consecutive angles have to add together to be 180. So if this is 90, we have exactly 90 degrees left for those consecutive angles, which also must be congruent. So once we start off with a single right angle, it forces all of the others to be right angles as well. All right, moving on, we're going to have additional information about our diagonals next. So we already know that diagonals bisect each other. So when we have that double diagonal drawn into a parallelogram, we are able to think about this point right here as being the midpoint of both of those diagonals. But when we are in rectangle mode, we have an additional piece of information that says that the diagonals themselves are actually congruent. And so before, we used to mark these pieces of the diagonal one way and the other pieces a different way, like with a double tick. But if this diagonal distance is the same as this one, congruent full diagonals, that actually means that all 4 of those small segments are identical. That actually leads us to our next property. If all 4 of these segments match, then we have 4 triangles inside this rectangle that end up having 2 congruent sides. 2 congruent sides. 2 congruent sides. So if you think back to what we learned about triangles in Standard 3 and Standard 4, not 4 maybe, but we've reviewed it a few other times. I just butchered that word triangle while I was talking, so let me fix that. When we have a triangle that has 2 congruent sides, that means that it's actually called isosceles. So we're going to have 4 interior triangles, now that I have that spelled correctly, that are all isosceles because of those diagonals that are congruent, but that also bisect each other thanks to those parallelogram properties. Okay, so all 4 of those interior triangles are going to be isosceles triangles. Now, there are a whole bunch of facts about isosceles triangles that might come in and help us out. So just as a real quick reminder about isosceles triangles, like I said, back from Standard 3, When we had an isosceles triangle, we knew two sides matched, but then we had the base angles theorem that told us that we could travel to the opposite angles, and those opposite angles would also be congruent. And so we're going to be able then, in our rectangles, to travel to the opposite angles, and these little parts right here are going to end up matching. We could do the same thing with the isosceles triangles on the sides. We could travel to those opposite angles, and those opposite angles, I'm just going to use dots to squeeze them in, would be congruent. Now, it does not tell us that these two angles back to back are congruent. That was a rhombus property. The diagonal bisected this angle. That does not happen in a rectangle, but we do have this isosceles triangle situation happening that gives us congruent angles, in a different way. Okay, let's go ahead and take a look at some examples of how all of these properties are going to be put into action. First things first, let's get the information provided onto the diagram in the correct spot. That's important because sometimes labeling is a little bit tricky. They are telling us in this first problem about the measure of angle BAC. So if we travel from B to A to C, that angle tucked into the corner here, up where that A is 27 degrees. Okay, if we are looking for the measure of angle ACB, ACB travels this direction and ends up creating this angle down here at C. So this one is our goal. How are we going to find the measure of angle ACB? Well, this is a part of an angle. So it used to be that when we had a part of one of those corners, we would think about alternate interiors. The alternate interior angle with this one, however, would be down here. So it's not quite the angle I'm looking for, but it is close. So we might think about that as a way to help us. Or we could think about how this entire angle here is a right angle, because I'm noticing that these three angles together form a triangle. So there's a couple different options we can use to help us figure this out. But I feel like we're definitely going to use maybe triangle facts from before combined with that right angle, or we could think about alternate interior angles and how this one is a right angle. But regardless, we're definitely focusing on how a right angle from up above can help us out. I'm going to focus on that triangle. So I know that 180 would be the total of that 27-degree angle they gave me, the 90-degree angle up there at B, and then the question mark angle that I'm trying to find. So if we add these together and then subtract from 180 degrees, we should end up with the measure of angle ACB equal to 63. Now, if that does not seem like something that you are going to be able to understand, or it just kind of feels awkward to you, the other option is to think about how this whole angle is 90, and that whole angle is made out of the one that I'm looking for and the alternate interior angle to that 27. So we could copy that 27 down there to the bottom. So we could also solve for our question mark angle by using a little angle addition property, or postulate, back from standard 2. These two small angles add up to be that whole angle. So then we could subtract that 27 and we would land in the same place with that angle we're looking for being 63 degrees. Often with rectangles, there are multiple ways to think about finding what they've asked you to find. All right, on to question number 2. This time, we have the measure of angle BCA. So if I'm looking at angle BCA, that one is 78 degrees. This time I'm asked to track down the measure of angle DAC, and I'm noticing as I'm highlighting that out that angle DAC and angle BCA are alternate interior angles. So I'm using a parallelogram property this time That was the first property we wrote down up top. If these opposite sides are parallel, then those alternate interior angles are congruent. So the measure of angle DAC is going to be 78 degrees. Sorry about that. That doesn't really look like a 7 there. So 78 degrees. All right, moving on to example 3. Looks like we have another angle given to us. This time we're looking at the measure of angle ADE. So this corner here is 74 degrees. And the one I'm looking for is the measure of angle BEC. That is strange. Those do not look like alternate interiors. And because this angle that I'm looking for is in the middle of the shape, I don't know anything about 90-degree angles in the middle like I did with a rhombus. So I think we're going to have to be a little bit more creative with this one. I could take this 74 and move it over here using my alternate interior angles. That would be a little bit closer to the angle that I'm looking for. But I think I'm going to have to combine that idea up with the isosceles triangle fact that we talked about up top in reason number 4. If this triangle is isosceles, then that means that this angle and this angle are opposite and congruent. Those are the base angles for that isosceles triangle. So if I'm trying to track down this angle here, and 2 angles inside that little triangle are already both 74, I can take 180 and subtract those 2 74-degree angles to figure out what that leftover one would be equal to. We used to do isosceles triangle problems like that kind of frequently when we were back in Standard 3, but it has definitely been a while since we have seen that idea. So if we take care of that, it looks like that missing angle is going to turn out to be 32. I wrote my work in kind of a weird spot. I suppose it belongs down here actually, but that's okay. That means the measure of angle BEC, that one in the middle there that I was looking for, would be equal to 32 degrees. Thanks to that isosceles triangle fact helping me out. All right, one more example on this side of the page. This time they're starting me out with an angle in the middle of the picture. The measure of angle AEB is 144 degrees. My goal is to track down the measure of angle CAB. I think rather than highlight that whole thing, that might be a little bit confusing for our brain. I'm just going to focus on where that angle actually is, which is right there. That's the one that I need. And so I think this is going to be another opportunity for me to use that isosceles triangle fact to help me out. If this segment is equal to this one, that means that this angle I'm looking for is actually identical to the other one that I'm missing in that triangle. And so if we were to take 180 and remove the 144 degrees that we've already used up for this angle in the middle, that leftover amount of degrees is going to get split up evenly between those 2 congruent angles. So we can divide that number by 2, and that should tell us what that mystery angle is going to be equal to. 180 minus 144 is 36. So then when we divide by 2, we're going to get 18. So the measure of angle CAB is going to be 18 degrees. So that same isosceles triangle fact, but kind of used in reverse. Instead of knowing the 2 angles that match and finding the third, we knew the one that was different, and so we needed to subtract that away and then divide up those leftovers into 2 equal parts to make sure we could track down those 2 other angles in that isosceles triangle. All right, go ahead and flip over for the examples on the back, and I'll meet you back here in just a minute. All right, looks like we have 2 examples left, and both of these involve algebra. So all the problems that we did on the front side of the page, we were just given angle measures and we were looking for other angle measures. Those could have been algebra problems as well, but we just tried to keep it simple as you're getting used to these properties. But this time, we're not dealing with angles, we're dealing with segments. So if I know that AC is 4x minus 54, that is the entire diagonal. So I think I'm just going to color code that AC is that whole distance. And then BD, color code that one yellow, is this whole distance. Now, if this were just a parallelogram, or even if this was a rhombus, we would be stuck because we don't know anything about this whole diagonal compared to that whole diagonal in those two shapes. But because this is a rectangle, property number 3 on the other side tells us that our diagonals are congruent. And so even though these are different diagonals, they are whole diagonals. And so that means we can take the whole diagonal AC and set it equal to the whole diagonal BD. I'm going to subtract that 1x over to the other side so that all of the x's are together on the left. That means I'm going to be adding 54 over to the right side. 3x is equal to 87. Divide both sides by 3, and x turns out to be 29. Because I'm doing an algebra problem here, I'm always going to remember to go back and double check that I've taken care of what they've asked me to take care of. So I have found x, but I still need to track down one more thing to be able to finish this one out. So they are asking us to BD, which means 33 plus 1x is going to be the goal. 33 plus 29 is going to be 62. BD is a segment, so you do not want degrees as a label on that. If we knew whether these were inches or feet or centimeters or miles, then we would be able to label our units here. But otherwise, the length of BD turns out to be 62. All right, last one, number 6. Let's see what we've got going on here. For number 6, it looks like they are again giving me AC, that whole entire diagonal. And then the second piece of information changes a little bit, and it is DE. Now again, if this was a parallelogram or a rhombus, we would be stuck because there is not a relationship about different diagonals. We always had to stick to a single one. But remember that in a rectangle, all of the diagonals are congruent. And so what I notice is that this yellow one is going to match AE, but also CE. So it would take 2 of those yellow ones to total up to be the same as that whole diagonal AC. AC has 2 of those ticks on it, DE has 1, so it takes 2 of those to make that whole distance happen. Use your distributive property to multiply and get 2x plus 10 on the left side of that equation. We are again using the fact that the diagonals are equal to each other for that, with a little bit of the diagonals bisect each other as well, or I suppose you could have called that the isosceles triangle thing. There's lots of kind of things going on here. Not right angles, so definitely not that one. Subtracting 2x will move all of your x's over to the right this time, leaving with a positive 10 on this side. Adding that 60 over will make our equation look like 70 equals 2x. Divide both sides by 2, and x turns out to be 35. Do a quick double check. Looks like we've got half of what they ask us to, so we're on the lookout for what EC is equal to. EC is right here on the orange, but I know the whole orange segment. I don't know that part. So we have 2 options. We could find the entire orange diagonal by plugging in our x, but then dividing it by 2, or because these are congruent, it might be a little bit faster to find EC just by using what we know about DE. They're congruent, so that x plus 5 should work for EC as well. So if we take our 35 and we plug it in, it looks like EC is going to turn out to be 40. Again, no degree symbol because we're dealing with a segment. And that should take care of both of the things they asked us to find for example number 6. All right, that does it for today's In Class 38. Thanks for watching. We will see you back in class.